There's something.
All right, so we have 2 questions left in 13.5. We'll finish up those, then we'll go over a few of these homework questions and see where we're
But I
at.
didn't get the number, sorry.
Module due this Wednesday. Don't forget. All right, so this first question that we're going to do in 13.5, number 70, we've got a hemisphere, and the radius of that hemisphere is 2, and we are going to drill a hole in this hemisphere of radius 1, and we want to find the volume of what's left. Okay? So let's draw a picture, like a cross-sectional thing, just to get an idea. So we have something like this. We're going to drill the hole out of it. And that dimension is 2, so 1 is going to be about right there. And we want to find the volume that's left.
Isn't it a radius one, not a diameter one?
The radius is 1, so the diameter is 2. Thank you. Yeah, so we'll move those guys over. Thank you. So that kind of thing. And what coordinate system are we going to use?
Definitely cylindrical.
Polar for the domain, which means cylindrical. If we're in 3 dimensions. Cylindricals, cylinder coordinate system. So the volume, if we imagine our domain down in the xy plane, the r values are going to go from 1 to 2. We're dealing with an annulus down in the xy plane. Anyone have a question about that? Down in the xy plane, we're dealing with an annulus, and we're looking for all those values between 1 and 2. So we're dealing with something like that. There's our domain down in the xy plane. Make sense? So we want to do upper surface minus lower surface. So the upper surface is that hemisphere. The lower surface is the xy plane. So we're going to plot, and do we want, I guess, we don't have to use a triple integral. A double integral of upper minus lower is the same as a triple integral.
Yeah.
Right? So the upper hemisphere, if the radius is 2, let's write that equation first in x's and y's, and then we'll x, y's, and z's, and then we'll solve. So sphere of radius 4 looks like that. So the upper surface, if we solve for z, is going to be 4 minus x squared minus y squared, all positive square root for the upper hemisphere. And the lower surface, again, is just the xy plane. And let's convert over to cylindrical. So our volume is going to be the square root of 4 minus r squared. The lower, again, is just 0. And then we have r, and our polar differentials are r d theta.
Why is it not r d z?
Because we did a double integral instead of a triple. If we did a triple, it would be r d z dr d theta, but then that would be in the limits.
So you just eliminated that step. Okay.
All right, a double integral of a function is the same thing as a triple integral of nothing. Yep.
That was just what my question on is if you could maybe, you could use a triple in this one.
Mhm.
Can you?
Yep, we could just do that, and that would be our triple,
Okay.
where this whole thing
And
is
it'd be
shifted up.
RDZ, dr d theta.
So
Then
then
we
you're-
have a z in there to represent z equals the
Okay.
hemisphere. Yep.
Okay.
So a double integral of a function is the same as a triple integral of nothing. And let's just put one example up here just as a reminder. Like if we wanted to find the area beneath F, we would just do that. And that would be the area beneath the curve F. That's going to give us this area. Or we could do a double integral and go from 0 to f of dy dx. Those are the same thing. So a double integral of nothing is the same as a single integral of a function. Triple integral of nothing is the same as a double integral of the function. So then we have to grab our limits then. So we look down at our xy plane right here, and we see that the radius is going from 1 to 2. And the theta will go all the way around, so 0 to 2 pi. So that will give us the volume of what's left if we core out a 1 radius, a 1, whatever the units are.
Did you say radius?
1 radius, I was going to say radius. I don't know what I was going to say. I realized there was no units in the middle of what I was trying to say.
I realized.
We love these math problems, right? We never have any units. Well, not never.
Makes it very hard to double check to make sure you done everything right.
Right. Unless we're in the physics applications, then there's units everywhere. Okay, so any question on the setup there? Because that's obviously the most important thing.
Do we divide the z by 2 since it's a hemisphere?
No, because z equals the positive square root is just the upper hemisphere.
Okay.
So if we wanted to deal with the whole entire thing, we would go from minus square root to plus square root instead of 0 to plus square root.
And would you have that function inside of the derivative? So you'd have square root of 4 minus r squared minus square root of 4 minus r squared? How would you do that?
Say that again.
So would you put that into the limits, or could you put it into the function we have for
If
the
you
upper and lower? If we did
so
the whole thing.
so our next step is just to integrate this with respect to r. So we'll have to use the.
But if you did the whole
sub.
thing, would you just put minus
Oh.
square root of 4 minus r
We
squared?
just double it.
We just double it.
Yep.
Okay.
Because we'd have positive square root minus a minus, which would make it plus, and so that's essentially just doubling it. So if we were going to deal with the whole sphere, we would have a 2 out in front there.
Okay.
Yep.
Thank you.
Because you'd have square root minus a minus. So this would be the upper hemisphere minus the lower hemisphere is right there. And so then you would end up with that. So you'd end up with that.
Okay, thank you.
Yeah. Okay, so u sub. We're going to let u equal 1 minus r squared. So du is minus 2 r dr. So let's just fiddle with this. Instead of writing out the whole u sub, let's just be creative here, just like we normally are. Creative.
Like we normally.
Like we normally are. I'll put in a minus 2 there, and then I'll offset it by putting a 1 divided by minus 2 out in the front. And then we have u to the 1/2 du right away. If u is 4 minus r squared, then du is minus 2 r dr. So that just avoids writing out that whole substitution step. Do we need to keep the theta integral, or can we can collapse it? Squish it like a bug. And then in our integral, we're going to be integrating this thing right here. We have 4 minus r squared to the 1/2. So we get 4 minus r squared to the 3/2. 4 minus r squared to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. 1 to 2. And we get a little bit of cancellation. And we will be there shortly. That's minus 2 pi over 3 on the outside. Plugging in the 2 gives us 0. Minus 3 to the 3/2. That's 3 root 3.
Yes. No, that one.
Yay!
Hey, look, 2 negatives equals a positive.
2 negatives are positive.
Wow.
The 3's cancel. This is amazing.
This is amazing.
This is amazing. So then we end up with 2 root 3 times pi. So that'll be our volume.
Nice.
Enjoy it.
I like it.
2 root 3 pi.
We know what's coming.
Units cubed. No units. We know that they're cubic
volume.
units. It's volume.
It's positive.
It's positive. It better be positive.
Better.
That's
That's a good stretch.
good. Question?
Can we just set up the triple so we can see how we would do it with a triple?
So the only thing we would have done, we'd have this, 0 to 2 pi's, 1 to 2, 0 to square root 4 minus r squared,
Okay.
and then
RDZ.
RDZ, the
Okay.
RD theta.
Cool.
And that is a, that's a 0.
Would you specify whether you want to include 3 integrals or
Because it just turns into that, doesn't it?
I'll specify.
Almost.
All right, let's do an interesting one. So this is kind of a classic Calc 3 problem. Every book has it. The intersecting cylinders, we want to find the volume of the solid that's shared by both those cylinders. And that's what the image, that's what the object looks like, the solid object that we're trying to find the volume of. So we have to be really clever here. We need to first decide whether we should use lower and upper, left and right, front and back. There's 2 of those 3 choices that will work. Which one will not work?
Top to bottom.
Top to bottom does not work. So we want to do front to back. So here is the unique front surface. The unique back surface is back there. And there is a unique left and a unique right. So we can either go left to right or back to front. Doesn't matter.
Why is the top and bottom not unique?
So, right, that point right there. So if you move this direction, this is on top. But if you move this way, this one is on top. So those two cylinders are coming up, and they're different, right? That's a different top than this is.
Oh, okay, gotcha.
So we can't go top to bottom on this one, unless we were to subdivide and use a whole bunch of symmetry. You could, which you could do actually, but
Let's not.
Let's not.
no, that would be a lot harder. Definitely a lot harder.
Not today.
So front to back or left to right? Left to right. So if we're going to go left to right, that means we're using y surfaces, y equals, y values. So, and let's definitely use some symmetry. So we're going to think about this surface over here as the right surface. So let's come up with an equation for that right surface. Let's see. So cylinders each have radius of 1. So what will be that cylinder, that right cylinder? We're in the xz plane, so what would the equation be for that cylinder?
X equals Z, or Z equals
Y
Z
y
equals
squared
X
plus Z squared
squared.
equals, what is it, 1?
So let's write both cylinders down. So both cylinders, the one that is, if we write down both, then we can sort of probably see it more easily. So each of them is a cylinder, so one letter is missing from each. So in one of them, the x is missing, and in one of them, the y is missing. So we're going to have x squared plus z squared equals 1, and we're going to have y squared plus z squared equals 1. Those are the 2 cylinders. So this one is the one that's opening in the y direction, but that's not the cap. So this is acting as the lateral bounds, the sides of the surfaces that are left-right surfaces. The actual right surface is going to be down here. So this will be the right surface. Positive square root 1 minus z squared. This is the right surface. And the left surface would be minus the square root of that. So if we wanted to not use symmetry at all, we would use this as the left surface. Okay, so these are our 2 surfaces. So our domain is going to be in which plane? If we're going to use that surface, the y equals, our domain is in the xz plane. Right? The y surface is defined on the xz plane, just like surface that z equals something is defined on the xy plane. So it's defined on the plane that's missing that dependent variable. So we're going to look at our xz plane as our domain. And our xz plane has the domain that is the other cylinder, essentially. Right? So in the xz plane, that's going to be our domain, circle of radius 1 centered at the origin. That will be us. Circle of radius 1, centered at the origin. Okay. All right. So we have to be really careful. One direction is going to be hard to integrate. Another direction is going to be easier. So it's going to be very easy. So let's look at both. So let's set this up. Do you agree that we could use a whole bunch of symmetry here? Do you see that we could really just focus on octant 1? And if we focus on octant 1, we're going to get 1/8 of the total volume. If we focus on octant 1, there's going to be 4 chunks above the xy plane, 4 chunks below, and in each octant there's going to be 1/8 of the total solid. So we could definitely use some symmetry here. So let's do that. We're going to multiply by 8. So we're just going to go with octant 1. And over here, we're going to figure out our order. The dy is determined already. We've decided left, right. Now we can either go dx dz or dz dx. So let's look at both of those. So we can either go this way, or we can go this way. Now one of them is going to be bad, one of them is going to be good. Let's figure out what makes the bad, what makes the good. Both of them are going to have the same limits for the inner integral. We're going to go 0 out to the positive square root of 1 minus z squared. Okay, so now in the domain over here, let me move this. Let's just move that out of the way, because we're going to be, bless you, we're going to be dealing with that first quadrant there. Okay, with this setup here, dx dz, are we choosing to use a vertical element or a horizontal element over here? We're just focusing on the first quadrant here since we are using symmetry.
Horizontal.
So horizontal element, everybody agree and clearly see that that's a horizontal element for this right here, dx dz. Z's on the outside, which means z comes from a constant interval, and the constant interval is always perpendicular to the element. Okay, so then we would set up 0 to 1 for those constant limits. There. And then how about the x limits? The circle is x squared plus z squared equals 1. So what is the right curve?
Root 1 minus z squared.
Mm-hmm. So that will go right there. Around. Okay, so is this an easy integral or a hard integral to evaluate?
Hard because it's a square root and a square root. No, it's not.
Yeah.
Never mind.
Hard because it's horizontal. I think it's easy.
Because you
So is there a y in here?
No.
No, so we collapse. We get square root of 1 minus z squared. Is there an x? No, so we collapse. We get square root of 1 minus z squared, square root of 1 minus z squared. Those combine to be just 1 minus z squared dz.
And then multiply by 1.
Right, so we get this. We still have to integrate, though. We're still going to have to integrate with respect to z. But the inner integral is just collapsed to this. So this actually is the easy way. Now let's notice why the other way is not easy. So with the other way, it is not easy. We would have the x's coming from the constant interval 0 to 1. And then what about the z's? If we chose a vertical element here, we'd go 0 raised up to 1 minus x squared inside a square root.
Now we have lots of variables.
We have lots of variables. So when we pull this down, when we do our first stage of integration here, the outer two integrals stay, but then we have this. And this is going to be really messy with these limits up here. That's hard. So we'd have to use trig substitution, and it's going to get really, really messy, fast. This one, though, this one's piece of cake. This one, we integrate. We have 8 out in front. We get z minus z cubed over 3, 0 to 1. So we end up with 16 thirds. So that way is a lot easier than the other way. Yeah.
So when we're doing these and we're setting it up and we find that we've got lots of variables and stuff going on, but we've got lots of symmetry, should we try to like reevaluate and see if we can set it up like an easier way?
There's always, if you can use symmetry, it's always going to help. If you can have zeros in the bottom, it's going to help.
Yeah.
So I would say the thing that we have to be careful of is symmetry based on the shape of the object versus symmetry on the function. So we're going to be doing some stuff today where we find the center of mass of an object, and it's like, oh, well, the object is very symmetric. Maybe it's a disk. But it's not the object symmetry that matters. In that case, it's going to be the density function symmetry. So we just have to be careful when we talk symmetry. Here we're purely talking about the symmetry of the object, and that's fine, because we don't have an auxiliary function that's defined on that might not be symmetric on this symmetric object. Right? You can imagine a disk with density being different at different places, and that's going to matter then. Half the disk might weigh more than the other half. So we just have to be careful when we talk symmetry that we're identifying whether it's the object or the function. In this case, we don't have a function. Okay, so questions on any of that setup? Is everybody clear on how this just collapses down, these two inner integrals? There's no y here, so the inner integral turns into just square root of 1 minus z squared. But then there's no x, so that integral also just collapses. Because the integral of a differential is the length of the interval. All right, so that's how those two go. And now, if we did select, instead of doing the left and the right, if we did select the front and the back, we'd have the same situation. One of the directions is going to be really easy, same type of thing. The other direction will be hard. You'll have to use a trig sub and be pulling out your hair. Okay, so someone asked about this one from 13.2, I believe.
Yep.
And what was the question on this one?
This one, I just kept getting it wrong. I just couldn't figure out where I was getting it wrong.
Okay, so it looks like we want to find the average value of that function over this region. Let's first draw the region.
And I did one before, it was like 9 minus x minus y, and that one was fine, and I think maybe it's just because there's,
In A?
yeah.
Let's find out. Okay, so this is just y equals negative x plus a. So to me, that looks, we can graph that pretty quickly. If we're thinking about that x-intercept is a and that y-intercept is a. Is everybody okay with that? So that's y equals negative x plus a. So y-intercept is a, slope is -1. And then we're going to look just at the region inside this triangle. And a is going to be bigger than 0. So then the area of R, so area will be the double integral dy dx, or we could do single integral of a function. It's not going to matter. Let's just do it as a double first. So the area, the x's are going to come from 0 to a. And how about the y's? So vertical element, the x's are coming 0 to a. So then we're going to go up to the line. So we're just going to have 0 up to this line where we solve for y. So that's going to be negative x plus a. So that'll be the area of the region. Now it says we want to find the average value of this function. So we have to find the average value of that function by integrating it and then dividing by the area of R. Right? Average value is integral of function divided by whatever this area is. So the function is a surface on top of this triangle. So we're going to figure out that next. So double integral of a minus x minus y. Let's just go dy dx again. And the domain is right there. So are the limits any different than those limits? No. Now we're integrating this function on that same domain. So the integral of nothing is giving us area, whereas the integral of the function is going to give us volume. Double integral of nothing is area. Double integral of a function is volume. So y's are going to go 0 to minus x plus a. x's will go 0 to a. And then we'll integrate that with respect to y.
Okay. I get
So try that and just see if that works out.
it. No, I see what I did wrong.
Oh, good.
Thank
Good, good, good.
you.
And then we divide. Divide that by that, and we'll get to it. All right, let's take a look at this one. 13.3, number 12. So it says, find the volume of the solid. The solid is bounded by the paraboloid and a plane. Does this paraboloid open up or down? Everybody agree down? So we've got, if you plug in x and y equals 0, you're up at z equals 6. And then it's minus x squared minus y squared, which is going to drag those z values down. So we have an upside down paraboloid. That's the upper surface. This is the lower surface. Okay, so we've got that down to the plane, z equals 3. So set up the double integral and polar to find the volume. So the volume will be the upper surface in polar. So that's in polar then. Everyone agree that that's in polar? X squared plus y squared is r squared. So if you factor it out, this 3, you'd have 6 minus 3 times x squared plus y squared. So there's the upper surface minus the lower surface, and then r dr d theta. So we have upper minus lower. So if we wanted to do this as a triple integral in cylindrical, the innermost integral would just have this as the lower limit, and that is the upper limit. And then you'd have a triple integral in cylindrical, and we'd have to add a dz. Will?
And yeah, this is the last problem of the 13.3.
Pardon?
Yeah, is this the last problem the 13.3?
This is in 13.3, number 12, yeah.
All right, all right. Because the one I was thinking of involved trying to. You had 3 different surfaces, and you had to find the volume of my code.
That was
the second to last one, I think.
That
That's the last one. 13.3?
Yeah, this was the last problem. The other one was like the, you're talking about like the paraboloid, the cone, and the hyperbola.
Yeah.
I got
Yeah.
that as the last one too.
Oh, so is this the wrong problem?
Yes.
Yeah.
Oh, okay. Is this one too easy?
Yeah.
Oh, I have a question though.
Yeah, you have a question on it?
Yeah, I just wanted to check, I think you said this last week, is
Yeah.
that when we're in polar, we're always doing upper minus lower.
Yeah.
There's no funny right minus left, back minus front, south minus west, okay.
Because
Yeah.
you're always going to do RDR theta.
Yeah, 99% of the time. You
Yes.
could, 99% of the time with a polar domain, it's going to be in the xy plane, and you're going to do upper and lower. It'd be just a little complicated if they were doing polar
Just a
in the
little.
xz or the yz. So I think I haven't seen a single problem in this book where they do polar with a different orientation. Okay, so just to finish it off, though, what are the limits? How do we find the limits?
Set that equal to 0 and solve for y.
Yep, exactly. And so what do we get when we set that equal to that? We get 6 subtracted over, so we get minus 3. We divide by minus 3. We get a circle of radius. 1. Yes, dividing by negative 3 gives 1. Negative 3 divided by negative 3 is 1.
But isn't it negative 6 on the other side?
So when you set those equal to each other,
Oh, when you set them equal.
subtract the 6, and that makes it a
Okay.
negative 3. Divide by negative 3, and you get x squared
I
plus y
missed
squared
the
equals
setting
1.
equal to each
I
other.
have just a quick question about
Sure.
like, the on the d theta limits. So sometimes I think there was like a problem I had that it was like 5 pi over 8 or something, some angle like that we don't know. If we had something like that, would we just do like, because it wanted an exact answer, so I had to give
It wanted an exact answer,
Yeah, I
and
can't
5 pi
remember.
over 8.
It was like 5 pi over 8.
But a non-special
It was something
angle.
that I didn't know the. It was something.
Then you just have to leave it as cosine of 5 pi over 8.
I think it was tangent.
Or tangent of 5, you just have to leave
Yeah,
it like
and
that.
so just leave it like that
Yeah.
if we got a problem.
Tell me, I want to see that one. So
find it.
look that one up and email
Yeah.
it to me so I can look at it. So the one,
Yeah.
this was in 13.3, but it's not the one you guys wanted to look at.
No.
13.3.
Mine was 13.4. I
No,
know.
it was
No, it was
13.3.
definitely, I
And
got
it
it
was
as
number
number
12.
12 too, yeah.
Yeah, it was number 12.
Yeah, I might have accidentally, sometimes when you go into it,
Yeah, it was this one, like which holds with more water, and then it gives you 3 different.
I probably just grabbed the first one and thought I went to
Did I get
12.
breastfeed?
Nope.
Yeah.
There we go.
That one.
Yeah.
Well, I did it. I just got lucky, I think.
Yeah, this one.
I just got lucky.
It's
I
true.
just-
I
Yeah.
just got lucky.
Yeah. I'm not gonna sit there for hours if it gives me the same numbers.
Yeah.
And-
Sometimes you have to be strategic. I agree. All right,
There
so
Yes.
all right, so it looks like we're just trying to figure out which bowl holds the most water.
Yes.
It's actually not that bad.
Okay, so let's do this in cylindrical. The first one for the paraboloid, we've got a paraboloid. We're going from z equals 0, or the paraboloid up to z equals 4. So parabolic bowl. The volume of that first one, we'll call it V1, is equal to. So do you want to use a triple or a double? Oh, we don't have triples yet. Thank you. Okay, doubles. All right, so the upper surface is. So we get this.
We don't have
And we don't have triples. It makes it so much easier. Everyone agree with this?
Oh, tell me how you got that. Oh no.
So the upper surface is z equals 4. The lower surface is z equals r squared. So upper minus lower, and then
Well,
polar.
that would explain why I got mine wrong.
There you go, right there.
Yeah.
Where are you pulling the 2 from in your first integral for the boundaries? Shouldn't it be?
So if we set the two functions equal to each other, so we get, if we set them equal to each other, so when two surfaces are intersecting, if we eliminate the z, we've taken the curve of intersection and projected it down onto the domain.
Gotcha, I see where you're going to.
Make sense?
Awesome.
All right, this one's so hard. Okay. I mean, it's amazing. These
Making us
things,
feel
you can
so
bang
good.
your head against the wall, and then you sit and you're like, oh, why was I banging my head against the wall? Okay, so now next one, we have a cone, and you see the cone opening upward, right? If you look at your traces, you let z be 0, you get z equals absolute value of y. You let y be 0, you see z equals absolute value of x. So you've got that cone opening up, capped at z equals 4. So again, we're going to do upper surface minus lower surface, and then arty theta. It's the week of Halloween. We were allowed to be corny, right? All right, it's the week of Halloween. So then we do the same type of thing. We let 4, and then, oh boy, now we get a much bigger domain. We get a disk of radius 4. So that's going to go 0 to 4. So that, right away, I would guess that that's bigger than the first one. All right, and then we go to the third one, the hyperbole. The hyperboloid.
It's the Super Bowl.
It
but like
doesn't sound
modern.
right. The hyperboloid bowl. The hyperboloid bowl.
I'd watch sports if they had it called the Hype Bowl instead.
The hyperbole.
That'd be cool.
I'd watch sports.
I'd watch sports then. Okay. So here, do we see that the vertex of the bowl is at z equals 1? If you were to plug z equals 1 in here, you'd get x squared plus y squared equals 0.
Oh, it's a point.
It's a point, right? At z equals 1, plug in z equals 1. So the hyperboloid is the lower surface. The upper surface is going to be z equals 5. So we're going to get 5 minus, and square root of 1 minus 1 plus r squared. So there's upper minus lower, and then arty theta. And now our limits of integration, the easy ones first.
Why don't we just solve that to be, hold on, 25 minus.
You doing it in your head?
4 minus r?
So we're going to square both sides and subtract 1.
Yeah.
So square both sides, we get 25 equals 1 plus r squared. So r squared will be 24. R is going to be positive, so we get root 24. Ooh. So 0 to square root of 24.
which is bigger than 2.
He just.
Yeah, and so then, I don't know, that is
3, 4.
bigger than 4. I would guess this is probably the biggest one.
It is, but
Yes, sir.
Yeah.
I was just gonna ask a really stupid question.
Oh,
as to
cool.
Why the R isn't squared? And
Which
the
R?
second one?
This one right here,
Yes.
that one up there.
Yeah.
So if we come up here, the square root of R squared is R.
Right.
For the last
I was
one, I
just
think it's
testing
4 minus square root of 1 plus r squared.
This should be a 4.
Yeah, because it's go from 1 to 5. This would be 4.
no, but the top surface is z equals 5, right?
Yeah, the top surface though is z equals 5.
So that's what you set it equal to when you tried to.
Because that other one accounts for the 1, right? The one up.
This one right here?
Yeah.
Yes, though this is already lifted up 1 unit right there
Right.
because of the 1.
Oh.
So the paraboloid doesn't sit on the xy, or the hyperboloid. It doesn't sit on the xy plane like the cone or the paraboloid. So it's sitting up at z equals 1, and that's taken into consideration right there. And then it's going to go up to the flat cap of z equals 5. So that will, yeah, so those will be the 3. And then integrate them all. The biggest number is the biggest volume.
It's that simple.
It's that simple. It's that simple.
Yeah, that's.
All right, let's take a quick look at this guy. All right, we're not going to go through this whole thing. We'll set up a triple integral to find the volume of the solid bounded below by the cone and above by the sphere.
Yes, this one makes sense to me.
Does it make sense now?
Yes.
You want to do it?
No, thank you. I'll screw it up if you let me do it.
Okay, so triple integral, so that makes it look like this.
Yeah, this one.
And what coordinate system are we using?
D, y, x.
Yeah, we don't have spherical yet, right?
Yeah.
So we're just going to use cylindrical. So in cylindrical, we do r dz dr d theta.
But the setup from the that homework is dz, dy.
Oh, they wanted
Yeah,
it.
it has
Oh,
to be
gosh.
Yeah.
That's the way I want.
Oh, okay.
Oh, that's why I did it that way. Yeah.
They want it in that way, but then after you
Then you
enter it
convert
in
it?
like that, then you can convert it.
Okay, so dz upper surface, we have to solve that for
That's how you have to
z.
put it in, but then
So this is
once
going to
you
be
put
the
it in like
square
that, then you
root
can-
of
and then
1.
just wait.
Wait, is that a 1 or is that a? Oh, it's a 450. That's not 1. Oh no. Oh no. Okay, well we know it's a 450. Do we? Right there. Yikes. Hopefully that goes away.
It doesn't look like it's.
Oh.
Never mind.
It's gonna be funny to watch later.
Okay. All right, so that, and then the lower surface is given to us already. Z equals the square root of the cone. So we've got that. All right, now we have to look down into the xy plane. So we need to intersect the two and project that curve of intersection into the xy plane. So we've got to set those two equal to each other. So let's go ahead and do that. So we're going to get x squared plus y squared. If we want to replace that with z squared, isn't that just another x squared plus y squared? Equals 450. Everyone okay with that?
And then we can probably 2x squared plus 2y squared equals 450 divide out of 2.
Oh, we like that. Circle of radius 15, centered at the origin. So y's are going to go from minus the square root up to plus the square root, and then x's will go minus 15 to plus 15. So, do you agree with that?
And we can use symmetry for the x's, right?
Well, they're not allowing us to use symmetry, right?
No.
So if we were to evaluate, yeah, we would definitely use some symmetry, but they're not. They want us to just set it up like this.
You have to enter it in as your negative on the bottom and your positive on the top.
So we're using a vertical element, and the lower curve down here is going to be y equals negative square root of 25 minus x squared the upper curve will be positive square root of 25 minus x, 225 minus x squared. 225 minus x squared. So that would be our setup. No questions?
I solved that.
Solve that.
Yeah.
I can't believe Haley doesn't have a question. It's so surprising. Oh, do you have a question?
Yes. The x squared plus y squared, the extra one, where did you
Yeah.
get that again?
So right here we have 2x squared plus 2y squared, so we divided everything by 2.
But where did you get the z equals x squared plus y squared?
So
Is it a root?
that came by setting these two by doing a substitution. So if we have two surfaces, we plug one into the other to get the curve of intersection.
Got it.
Make sense?
Yes.
You
Thank
just
you.
didn't show the.
I just said it 3 times. Zinger. All right.
So fine.
All right. So then, if we change it to cylindrical, what's going to go on the inside here?
RD.
Yeah, r d z d r d theta. And then the z's, we're going to convert both of these over to. Yep. So we're going to
Square root
have
of
r.
450 minus r squared.
And then square root of 450 minus r squared. Bless you. And then how about the r's? 0 to 15. Thetas?
0 to 2i.
Yeah. Makes you appreciate cylindrical coordinate systems,
Yes.
right?
Very
That
much
looks so awful.
So we need to convert it. If we don't convert it, it's really
It's really almost impossible,
yeah.
Which is what I tried.
right? Because if you
Yeah.
if you put that in there and then try to integrate it with respect to y,
I tried that.
did you try?
I tried that. It doesn't work.
Because the setup is that,
It doesn't
so
work.
I think it doesn't allow us to convert it to.
It doesn't allow you?
I mean, it makes you enter it in that way, and then you can solve it.
Because in the very end, they just ask you for the actual volume, right?
Yeah.
So, yeah.
That's what you
Yeah, that you definitely want to convert
Right,
that
you
to
did that.
cylindrical.
I'm not just saying that.
Okay, let's take one quick look at this last one, then we'll get moving
I
on.
entered it in this way and then converted. Yeah, you can't.
So this one says find the volume of the following solid using triple integrals. So should we use lower, upper, front, back, left, right? Lower, upper?
Yeah.
Definitely lower, upper. We have a unique upper and a unique lower. So we'll definitely do it that way. And it says to use a triple integral, so we'll do what they tell us to do. And if we're going to use, are we going to use cylindrical right away, or should we start by setting it up without cylindrical? Start with that. Okay. So the lower surface is x minus 3. The upper surface is 3 minus x, and that's defined with z. So z equals 3 minus x, and z equals x minus 3. Okay, now we have to go down into the xy plane for the domain. That's already given to us. We don't have to set these surfaces equal to anything because we've already been told that the cylinder is the lateral bound. So we're going to go down into the xy plane and, or whatever that thing is. It's not quite, it's not a circle, but it's an ellipse. So that's down in the xy plane. So that's going to define the lateral bounds for this object. So if we graph it, we will have, first, when you're graphing an ellipse, the simplest thing, eliminate the x, get your y-intercepts, eliminate the y, get your x-intercepts so that you can see where your vertices are. So eliminate the y, we get x squared equals 9, so x equals plus or minus 3. So we know that we have those. Then you eliminate the x, you get y equals plus or minus 1. All right, so there is our domain. That's our ellipse. Close. Very close. Okay. Horizontal or vertical element?
Vertical.
Vertical, okay.
Vertical's easier.
Vertical is always easier. So we'll go vertical. So that means that we're going to have to go dy dz, excuse me, dy dx. X is going to go from where to where? The constants?
Or 2.
I think I heard the right answer in there somewhere. So x's are horizontally going across -3 to 3. Like?
Supposedly, could you ever pick like a way to integrate that wouldn't be exactly horizontal or vertical? Could you pick like some dynamic kind of like? Not saying that you would want to, but is that possible?
Yes.
How do you do that?
We're not going to talk about that. You can do that, but that's much harder.
Yeah.
And you would only want to do it, it's like we go to cylindrical when it makes sense, right?
Right.
We go to spherical when it makes sense. So use a slightly different type of integration when it makes sense. So as long as our domains are easily manageable without rotating anything, we'll stick with that. But there's these theorems called the rotation of axis theorem, which will allow you to convert between different coordinate systems. And we'll do something similar in the next chapter when we, or it's actually in, is it this chapter?
What?
Jacobians.
Oh yeah, that's like
That's
now.
coming up.
That's
Yeah,
like
we'll
today.
we'll get to something that's sort of like that soon. A little bit different, but kind of like that, where you switch your coordinate
This
systems.
problem is.
Okay, how about the lower limit then? What's the lower limit?
I don't like trig sub.
1 minus.
I
Negative
don't
1 minus
remember.
x squared over 9.
So we're going to have to solve this for y. So we get y equals plus or minus the square root of 1 minus x squared divided by 9. So that's going to be the upper curve and the lower curve. So the lower curve is down here. That's going to be minus the square root, 1 minus x squared divided by 9. And then up here is the positive square root. So that would be our setup without cylindrical, with kind of pretty gnarly boundaries. And if we wanted to set it up with cylindrical, let's convert it. And we'll still do a triple, so we're going to do z, dz, dr, d theta in there. And the z's on the inside, do those change?
No.
You think those change?
A little bit.
A little bit, because with cylindrical we have z's, r's, and thetas. We don't have x's. What is x equal to in cylindrical?
R cosine.
R cosine theta. Thank you. And down here we're going to have r cosine theta minus 3. And now r is going to go from,
Theta.
ooh, switch it. Are we supposed to switch to cylindrical here?
I'm thinking no.
I'm thinking no all of a sudden. How do we write this cylinder in cylindrical? Or this ellipse in cylindrical? Yeah, this does not seem like the way to go. I didn't read the rest of the question. Saba, did you read this one? I feel like... this to me feels like we're supposed to just keep going in rectangular, because this is not going to work here.
Yeah, it just says find the volume of the
Yeah,
solid.
going to cylindrical is not going to work here.
You have to have like some straight x squareds plus y squareds
Yes,
to go to cylindrical.
exactly. Yeah, cylindrical won't work here because we don't have x squared plus y squared. Yeah, so it'll work if the domain is circular, but not if it's an ellipse. You know, we don't have a clean way to do that. So there's no z here, so we would do the upper limit minus the lower limit. And then we're going to integrate with respect to y. There's no y's there either. So this could be
It
interesting.
actually gets
3 minus x minus the value of x minus 3. Is that 0 or is my mental math wrong again?
I don't think it's going to be 0.
Minus 2x.
Dx dy required trig sub.
So it's going to be minus 2x plus 6, I believe.
Mental math is wrong again.
So it's going to be this minus this. So it's negative x minus x, so that's negative 2x, and 3 minus minus 3 is 6. And now there's no y there. So now again, we're going to multiply by the length of that interval. Since there's no y, we're going to have minus 3 to 3. We're going to have negative 2x plus 6. Multiplied by the length of this interval. That minus minus that, it's 2 times that square root. So 2 times the square root of 1 minus x squared over 9.
That's
and
trig sub.
that's dx. So then we get to that.
I think so. I think it forced me to do trig sub.
So actually, let's keep going because
I did it the other way though.
you can avoid trig sub, I believe. At least when looking at this right now, I think I can avoid it. Maybe I'm wrong. Okay, so minus 4x square root So we get that. That part is u sub, and then plus 12. And I'm going to just rewrite. I'm going to separate this into two separate integrals just to keep it a little cleaner. And that's 12 multiplied by the square root. Let's put an integral there then. Minus 3 to 3. 1 minus x squared over 9 dx. Okay, we won't go through this u sub part. That you know how to do. So that's u sub. How about this second piece? You clearly could use trig sub, but is there geometry you could use there?
It's like
What is this integral representing?
the right half of the ellipse.
So it's x is going from minus 3 to 3, and then the function that we're integrating is the upper semi-ellipse.
So could we divide by 2?
So we are finding, so that integral is representing, oh, come on. So that integral is representing half the area of the ellipse. Is everybody on board with that? So this part right here, that equals area of the ellipse divided by 2.
Because of the square,
Because of what?
the square root.
This positive square root. So if we integrate the positive square root from minus 3 to 3, that's just going to give us the area between the upper part of the ellipse and the x-axis. And what is the area of an ellipse? What is it?
I don't want to say it because it's wrong.
I don't want to say it because it's
I
wrong.
think it's just the same as a circle. isn't
It's
it?
the same as a circle.
Higher squared.
Area of a circle is pi r. Both the r's are the same. Area of an ellipse, pi ab. So area would be pi times 1 times 3. So the area of this ellipse is 3 pi. So this whole piece down here is going to end up being 3 pi over 2. The blue part.
Can we do the trig sub?
I know we must have.
Yeah, let's do the
I'm not going to do the trick sub right now. It'll work though. You use sine.
Sine.
X over 3 equals sine of theta. It will work. It's just a little, it's a lot messier than that.
After class maybe?
Oh, I had a question.
Oh, that's a good point. I have to leave right after class today. My niece was hospitalized last night, so I've got to go.
Is she okay?
Yeah, she's got diabetes and she's doesn't take care of herself. So she has ketoacidosis and she got rushed to the hospital at 1 a.m. and was calling me all night long. Yeah, she's a mess.
Thank you for not canceling.
Yeah, exactly.
The whole trig sub thing. So I tried using trig sub on the homework, and I got an answer in terms of like arc sine, but it didn't like it. Because
Yeah, you would have to simplify that.
So if you like leave it in terms of the arc sine, it doesn't like that.
No, because because if you have a function that you can't evaluate, because you would have had arc sine of something you should have been able to
Like
evaluate.
3/5 or something. Yeah, like it was pretty clean.
Did it seem like it was not going to simplify to something normal?
No, I just like left the answer in arc sine initially, and then in the answer they wanted like square roots and stuff, so you had to go solve the arc sine.
Right,
But
yeah,
like
yeah,
if you
yeah.
use trig sub, you just have to simplify all this stuff.
So if you end up with arc sine of root 2 over 2, you've got to go back and turn that into pi over 4.
Okay.
I thought it was weird because sometimes it's picky about that stuff, and then sometimes you can write something absurdly long, and it's like
That's
it like expands
Fantastic!
the block to huge. And it's like good job.
Good job.
Yeah, we saw that today in the Math Center. Okay, let's get started on the next section, and then we'll take our break. All right, we'll get started on this section. We'll take a break. So here we're going to be finding center of mass and centroids.
This is like physics.
Does anybody know the difference between center of mass and a centroid?
Center of the 3D center.
Either one. Omar?
Center of mass is actually like the center of the main
Object?
mass. Object, yeah, the main mass. But the centroid is divided by like the x or divided by the y, divided by the z in a certain region to be in a certain area.
So basically a centroid is a geometric center of an object. And if an object has uniform density, then the
They
center of
equal each
mass
other.
and the centroid are the same. But if there's variable density, then the geometric center and the balance point are different. So usually with centroids and center of masses, it's usually easiest to imagine a two-dimensional two-dimensional surface, because you can imagine, finding the balance point where the plate will balance there, depending on what the density is. So geometric center is centroid, and then the balance point. So for a variable density, the balance point is the center of gravity.
Can you have a non-uniform density where the two would still correspond, like all density is is evenly distributed along the surface or something like that?
Yeah, you could certainly create a variable density situation that has the same center of mass as centroid. Yeah, definitely possible. And the center of gravity can also be outside of the object if you create some weird situations too. So.
And do you use center of mass and center of gravity interchangeably here?
Yes.
Okay.
But not centroid, it's center of gravity. Okay, so let's take a look at how we calculate the center of mass or the centroid. This board is looking very strange.
Just 30.
Yeah. You see that too?
Someone's
I feel like
then use the dry erase.
It looks like feathers.
Yeah.
Yeah, the one in the math lab was like that too.
Must be like
Stand
a
over here.
phantom.
Do you have any of that spray?
I'm not touching it. I see spray, but I'm not touching it. Okay. The integrals that we're going to set up are going to kind of be generated from these basic ideas. We're going to talk about a moment. So a moment is going to be mass times distance. So we're going to imagine this fulcrum right here. And in order to have a balance point, the moment here has to equal the moment there. The moment on the left has to equal the moment on the right. So the mass times distance on the left has to equal the mass times distance on the right in order to have balance. Okay, so that'll be the balance point when we have equality between the moments. Yeah?
It's the same as like a moment of inertia, right?
Yep. I mean, similar. Similar. Moment of inertia, I think, is slightly different than a moment about a point or a moment about an axis. So a moment of inertia, we're going to see in a minute that we can define a moment using an integral. And we use in that integral the distance to the object that we're finding the moment about, whether it's a point or an axis. And for a moment of inertia, I believe we look at the square distance instead of just the distance.
Okay.
Will?
Yeah, I haven't really studied this moment thing. What's the actual this moment mean?
Moment is mass times distance. You can think of it as a tendency to rotate.
Okay.
So if this moment is bigger than this moment, then the tendency to rotate is going to be, clockwise in this case.
So generally, moment is mass times distance.
Mass times distance, yeah. Nico?
For these problems, are we just going to assume that whatever the weights are balancing on are massless? Or are we going to have to do...
We'll...
Okay, cool. Because that would suck.
We'll keep it simple. We're going to keep it very simple. This is not physics. Okay, so let's talk about how we get the balance point here then. X bar is going to be called the balance point. That's going to be the coordinate here when we're on a coordinate line. So we're going to take the moment for this point right here. The moment is going to be its coordinate, its distance from the origin, multiplied by m1. Find the moment here, and we're going to divide by the mass to get the balance point. So we're basically finding some sort of average. If we were to multiply both sides of this right here, x bar multiplied by that, then we'd have a moment equals a moment, and that would be for that point right there. We'd have the moment on the left equals the moment on the right, so we'd have balance.
Just like above.
So this is very similar to the average value problems. We're going to take the moments and average them by dividing by the total mass. So we add up our moments, divide by the total mass, and that will give us our balance point. So moment divided by mass. That's all we need to remember. Moment divided by mass. We've already talked about this type of thing down here before, where back when we were doing the wires, we were integrating density to get mass. Back in that was the first chapter we did? Or second chapter?
I feel like it's in a number.
It was a while back.
I think it was in Calc 2.
It was on that first test. Oh, it was in Calc 2. It was a while back. It was a while back. like not in this class, where you were dealing with finding the mass of a wire. So we talked about linear density and area density. Typically when you think of density, you think mass per unit volume. But if you have a very thin plate, you can talk about mass per square area. Or if you have a thin wire, you can do mass per linear distance, mass per unit of distance. Yeah, so yeah, that was a while ago. Okay. All right, let's stop there. Let's take a break. Take a break. Take 10.
I haven't done a derivative yet. It's still delta y over delta x.
All right, let's roll. Let's do a few center of mass problems.
Yeah.
Just a few, not too many. Okay, so when we have the first one we looked at, we had discrete points. Now we're going to look at something where we have a continuous density function. And instead of adding up all the moments like we would with discrete point masses, we integrate to get the total moment or the total mass because we have variable density. So let's first take a look at this guy right here. The moment is going to be the collection of all little moments, so the collection of all distances multiplied by the corresponding masses. So right here, when we multiply these two together, we're going to multiply density times distance, and that's going to give us, and then when we integrate, we're going to get the total moment. So if you multiply density times distance, what do you get?
Say that again.
Density times distance. Mass. Density times distance, mass. And then mass times dx is a mass times a distance. So if we think about the units here, we have units of mass times units of distance, which are units of moments, and then we add up all those moments. So density multiplied by distance is mass. So it's probably, maybe it's more better to think about that as your density times distance to give you mass. And then the x is representing the distance to your fulcrum, or the point that you're trying to find the moment about. So then our units for the entire integrand, including the differential, units of moment. Mass times distance. Everyone okay with that? So over here, that is units of mass, and now we're just adding up all the units of mass to get the total mass. If we multiply by x, we're creating moments, and then we're going to add up all the moments to get the total moment. Moment, mass times distance. Okay, simple one-dimensional object. Find the mass and the center of mass for the thin rod with the following density function. So we're imagining just a thin rod, 1 unit long, and we want to find the center of mass for it. The density is not uniform, so let's first go ahead and find the mass of this rod. So we integrate density to get mass. And this is just one-dimensional, so the integral is pretty straightforward. Integrate that. Yeah, I'm having flashbacks. Back when math was so easy.
Wow.
Okay, so that'll be the mass of the object. Now let's find the moment. So the moment we have to multiply by x and then integrate again. So moment we take and multiply by the distance. X is representing the distance to the x is just representing the distance to each point along the way, along the rod. X is the distance from wherever we designate the 0 to be. So we end up with the integral of x plus x to the 4th, 0 to 1, x to the 5th, 5. So we get to that. What's that look like? It's going to be 5 7/10. So then
we have done this with a double integral?
Say that again?
Could you have done that with a double integral?
Not this one.
No.
Well, because here we're just dealing with a wire. So when we get to dealing with a lamina, which is an idealized thin plate, then we'll use a double.
Okay.
So here, just a single. And then our balance point, our center of mass, is going to be the moment divided by the mass, so multiplied by 4/5. So that'll be our balance point. So that'll be, yes.
Where you got that?
So x bar is equal to mass divided by moment. It's backwards. Moment divided by mass. We're averaging the moment. We're averaging the moment with the mass.
So you
we
just
take our moment, divide by mass. That's how we average our moment to get our balance point. So that distance x up there that you're thinking about is, sort of is just the distance to that balance point. Yeah.
This might be a dumb question, but the definition for the center of mass said that it is where rho is an integrable density function.
Mm-hmm.
What would be an example of a non-integrable density function?
Well, like if you had a function that you couldn't integrate. So like e to the minus x squared or something. So if you had some function that you just couldn't physically integrate. I mean, maybe you could numerically integrate it by approximating, but they're just saying that this function is going to be integrable. So, and that makes sense because when we think about, if we take an object and we think about the density can't change dramatically if you just move a tiny bit away. So the idea is that you've got some sort of density that's reasonable and easy to integrate. Because what's our condition for integration? So a function is going to be integrable as long as it's, well, there's some weird condition. Let's not talk about that. I mean, because even if it's continuous, you can definitely integrate it. But even if it's discontinuous at a finite number of points, you can still integrate it. So they're just saying that it's a nice function.
All right.
It's a nice function. We can integrate it. Let's not talk about when you can and can't integrate.
We don't talk about those kinds of functions here.
Because there are functions that are, weird, like nowhere differentiable but continuous everywhere. Like you can create some pretty funny functions. Okay, so you can have a continuous function that's nowhere differentiable.
But we're only gonna.
Yeah, we're dealing with friendly functions. Friendly functions.
Family friendly.
Family friendly.
Is that the one with
No piano curves.
She actually does the integral of e to the negative x squared over sigma squared. Or
No
something.
Coke snowflakes.
Like she's 7.
No
It's not like they
Sierpinski
sound
sponges.
These all sound fake.
The Sierpinski sponge is not fake.
It sounds like the Soviet knockoff of SpongeBob SquarePants.
The Sierpinski sponge. So that thing has, what the Sierpinski sponge has, what is its characteristics? It's got finite volume but infinite surface area.
Oh, that's so funny.
Finite volume but infinite surface area, just like the Coke snowflake has finite area but infinite perimeter.
Coke snow.
We did the Coke snowflake in Calc 2?
We did this.
No, we did the
We talked about it.
Gabriel's horn. Yeah, the Coke snowflake is the one where you
We didn't know.
you have the equilateral triangle and then you remove the middle third and you add more equilateral triangles there. And then you keep on doing that.
Oh, that's why it's a fractal.
It's a fractal.
That's why I've never heard of it.
That's why I've never heard of it.
My brain filters for fractals. Keep fractals away. Okay, so then let's go to 2 dimensions. So we have in math we call it a lamina. It's an idealized thin plate. We consider it to have no volume. No volume, but infinite surface area. Ugh. Okay, so we now have to define what we mean by a moment in this 2-dimensional situation. So if we imagine the balance point right there, the moment about the y-axis is going to include the x values. The moment about the x-axis is going to include y values. And if you want to find the moment about the x-axis, the y-coordinate of a point gives you how far away it is from that axis. All right, so if you're trying to find the moment about the x-axis, you're going to multiply by the distance a point is from the y-axis, or from the x-axis, which is its y-coordinate. So let's do this. So mass is simple, integrate density to get mass. We know that. So here are our moments. So the moment about the y-axis, we integrate density times distance to the y-axis, and the distance to the y-axis is x. Long story short, if that's a y, that's an x. If that's an x, that's a y. So the moment about the x-axis will be the distance to the x-axis times the density. Distance to the x-axis is the y value. All right, so that's all this next thing is saying. Let's try it. Let's see if we can keep it straight. All right, there are some curves that define a region, which we will call a lemma. So we have e to the x, exponential growth. We have e to the minus x, exponential decay. We have x equals 0, and we have x equals ln of 2. So let's call this ln of 2 right there. Okay, so we've got that weird region. And we want to find the mass and the center of mass, the centroid, because we're going to assume the density is uniform. So first, let's go ahead and find the mass. Mass will be the double integral of the density. So we're assuming that there's constant density. It doesn't matter what we want to use to represent it. We'll call, what do you want to call it? We'll call it rho, but we'll assume that it's a constant. We'll factor it out in a second. So if you want, you can just put a 1 there. Doesn't really matter. So how do we find this? Well, vertical or horizontal element for area.
Definitely vertical.
Definitely vertical. Definitely vertical. And then we are going to have dy dx for a vertical element. X's are going from 0 to natural log of 2. And how about the y's?
E to the x on top.
Yep, e to the x on top. So from decay to growth. And then we're going to assume in this case that rho is constant. And what will happen is that it's going to divide away in the end when we find our moment, when we want to find our center of mass. We'll see that it's just going to vanish. We'll just leave it there for now. We're going to assume it's constant. So when we do our inner integral, there's no y, so we get the length of the interval. So e to the x minus e to the minus x. Integrate that. We get e to the x plus e to the minus x from 0 to natural log of 2. Let's simplify that. So what do we end up with there? Looks like 2 plus 1/2 minus 1 minus 1, so that's minus 2. So we end up with rho over 2. So that's our mass, given the uniform density of rho.
That last row is so nice. No, actually second to last.
It's so nice row.
Do we need the row? You said you could just put 1 there, right? So it'd just be 1/2?
Because in this case, what we're going to see in a moment is that when you take your moment and you divide it by the mass, the rows are going to cancel. So if you assumed it was 1, it's going to divide out in the end anyway.
So 1 is okay, we don't need.
1 is okay. If you're dealing with uniform density and the goal is to find the center of mass, you can just assume it's 1 and you'll find the right point. You'll see where it's going to vanish in a second.
Sure.
We'll get rid of that beautiful row. Okay, so now let's find our moments. So first let's find the moment about the x-axis. So we have the same integral. Maybe I should say the same limits. And the moment about the x-axis, we have to take the density and multiply it by the distance to the x-axis, which is y. So that'll be the moment about the x-axis, the total moment. So every point here has its own moment. All right? It's density at that point multiplied by the distance to the x-axis, and we add up all those moments, and then when we divide by mass, we'll get the average moment, and that'll be the balance point, the center of mass. Okay, so here the row again, it factors all the way out to the front because it's constant. And we're going to integrate with respect to y. We get y squared over 2. Let's pull the over 2 out to the front also. So we have just y squared on the inside. So it looks like that. Plug in the e to the x, plug in the e to the minus x, and simplify. Rho divided by 2. 0 to natural log of 2. Okay, so we get e to the 2x minus e to the minus 2x dx. So that will be rho divided by 2. Here we're going to have e to the 2x divided by 2 minus e to the minus 2x divided by minus 2, 0 to natural log of 2. Okay, plug in natural log of 2. Let's be careful here. Let's pull out the 2 in the denominator. That'll help reduce error. So the 2's gone in the denominator. So plug in natural log of 2 there. Is that 4?
Yes.
4, and then we plug in natural log of 2 there, and we get 1/4 minus e to the 0 is 1 minus 1 again, right? So we will end up with, let's see, so 2 plus 1/4, so that's 8/4 plus 1/4, so that's 9/4, so that's 9 rho divided by 16. So that'll be the moment about the x-axis. Any questions on any step? So let's find the moment about the other axis, about the y-axis. Come back up here. Moment about the y-axis. Moment about the y-axis. So the only difference here is that we're talking about the distance to the y-axis instead of the distance to the x-axis, which means that we use an x instead of a y. So we get that. That'll be the moment about the y-axis. All right, so we integrate with respect to y. There is no y. If there is no y, multiply by the length of the integral. Let's pull the row out to the front. Multiply by the length of the interval, so we're going to have x multiplied by e to the x minus e to the negative x, egad dx. Ultraviolet voodoo. X e to the x. Ultraviolet voodoo. Here we go. U equals x. dV equals e to the x minus e to the minus x. dx. Let's squeeze this in here. So then we integrate, and we get e to the x plus e to the minus x divided by 2. I might have done that wrong. Should there be a divided by 2?
No.
I don't think
No.
so.
Yeah, we don't need that. All right, we're ready to apply it. So we have rho multiplied by UV. UV is x multiplied by e to the x plus e to the minus x. UV minus the integral of v du. And our limits of integration, let's get those in there. So 0 to natural log of 2 here, and this is evaluated 0 to natural log of 2. We can just hold off for a second on evaluating it and do it all at once instead of twice. Hopefully find a shortcut if we can. Okay, so here, x to the x plus e to the minus x. Maybe we can't find a shortcut. We'll find out. Okay, minus e to the x. And then e to the minus x integrates to itself, divided by a minus, but then you add, right? So it looks like that. Yeah, it doesn't look like we're going to be able to combine much stuff, so we just have to do it all out. Okay, so rho multiplied by, plugging in 0 there, the thing cancels, so that's good. So we just have to plug in ln2. So plugging in ln2 here gives 2 plus 1/2. Everyone agree with that? So we have natural log of 2 multiplied by 2 plus 1/2, 5/2. Next one, come over here. Plugging in natural log of 2, we're going to have minus 2 plus 1/2 up here. And then we subtract off what happens at 0, so that's going to be plus 1 minus 1.
I have a question. No.
Any disagreement? Minus 2 plus 1/2. Subtract off 1. Yeah, I think that's right. I see no reason at this moment to think it's wrong. All right. So final answer down here then is that we get rho multiplied by 5/2 natural log of 2 minus 3/2. Seems reasonable. Okay. So now we have all three pieces. We have our mass, we have our two moments. Moment about the x-axis, moment about the y-axis. So our whole goal is to find the center of mass. The center of mass is going to be, for the x value, we're going to take the y moment and divide it by the mass, and the opposite for the y coordinate.
That's the moment you said?
So m sub y is the moment about the y-axis. The moment about the y-axis divided by the mass is going to give us our x value for the balance point. The moment about the x-axis divided by the mass will give us the y-coordinate. So let's see if we can manage that. So m sub x right here, let's go with that one first, m sub y. So the mass is rho over 2. So rho over 2. So we multiply this by 2 over rho. Multiply that by 2 over rho. So the rho's go away. And so this is why I said that in the beginning, if you have uniform density, you can just assume the density is 1 and you're going to get the same answer. Then you don't have to write rho all the way through. M sub x, same thing. We are going to multiply by 2 over rho. So the rho's cancel, and we get 9 over 8. So that will be our center of mass, or our centroid. Lovely. Lovely ordered pair. Lovely ordered pair.
Is that not backwards? Why does the y come first?
So remember that the moment about the y-axis, we are using an x to figure out the moment about the y-axis. The moment about the y-axis is a tendency to rotate about the y-axis, which is an x coordinate. Right? So the moment about the y-axis is giving us distances from the y-axis. Moments from the y-axis, which dictate an x coordinate. Okay, so variable density plate. Find the center of mass of the following plane region with variable density. Describe the distribution of mass in the region. Okay, so we're going to look at a disk of radius 2 centered at the origin, but we're only going to consider quadrant number 1. Ooh, that's too big. That's left. Let's go that. Okay, so quadrant 1, we're only going to consider this part. So first, let's find the mass. And when we find the mass, we are going to do a double integral of the density to find the mass. First off, actually, let me say one other thing. Can we agree that the x value and the y value are the same here? So, in other words, can we assume that the center of mass has to be on that diagonal line that bisects quadrant 1? Can we assume that? Certainly the geometric center should be on there. But will the center of mass be on there? So we no longer can just consider we can no longer just consider the shape of the region. We need to look up here and decide, is that symmetric about this line also? And the answer is yes. If you come out here and you go over to there, the density there is going to match the density there, because we have x squared plus y squared. So the density is going to be evenly distributed on either side of that dashed line. So we can assume that the center of mass is going to be right on that line. So that'll save us a third of the work. All right, we definitely always have to find the mass. So the mass will be the double integral of the density function on our region. Now, do we want to switch to a different coordinate system? Yeah, let's do polar. It's two-dimensional, so we can do polar. So if we convert to polar, the inside is going to be 1 plus r squared, and then we have to multiply by r. So 1 plus r squared, r d r d theta. And when we look at our region, r is going from where to where? 0 to 2. And then theta?
0 to pi over 2.
0 to pi over 2. Good. So that will be our mass integral. So let's go ahead and distribute the r and integrate in the same step. Can we collapse the theta interval?
Yes.
Yeah, let's collapse that. So r times 1 is r. Integrate that, we get r squared over 2. R times r squared is r cubed. We get r to the 4th over 4. All right. Plugging in 2, we get 4 over 2, which is 2 plus 4, which is 6. So I think we get 3 pi.
Nice.
Does that look right? Okay. We'll go with that. That's our mass, 3 pi. Now we need to find the moment about the x-axis, the moment about the y-axis, or just one of them because we're going to assume symmetry. So we're assuming that our center of mass, I like to call it just C bar. Always writing x bar comma y bar is kind of a hassle. Just C bar, center of mass, centroid. Okay, so if we assume that x bar equals y bar, we can just find one of them. So let's go ahead and find the moment about the x-axis. The moment about the x-axis means multiply the density by y, because y is the distance to the x-axis. So multiply the density by y.
Are we going to stay in our polar, or are we going to go
That's my next question. What do you think we should do?
We could stay in polar.
So if we stay in polar, we're right over here. There's our polar integrand.
And then we multiply by r.
If we multiply by y, we multiply by r sine theta. So otherwise, we'd multiply this by y, and then integrate that. That still looks kind of yucky. I think we should go with this. So we have r times...
I'm getting something different than what we got.
Oh, let's
when
check.
I wrote down for the mass. I got 5 pi.
r sine theta. You got 5 pi?
Yeah, because r 2 squared over 2 is going to be 2, and then
2.
2 squared, 2 to the 4th over 4 is going to be 8, so it's 10 over 2.
Isn't this 16?
Yeah, so 16 divided by... Oh, it's over 4. I goofed. I thought it was over 2.
Oh.
Yeah.
Scared me there.
Sorry.
Terrified.
I'm not getting... I'm not getting 3 pi.
Not getting 3 pi?
Let's see. I'm getting 4 pi.
I got 3 pi.
All right. So now here we can't collapse our theta interval. We're going to have to integrate with respect to r first. So let's go ahead and see if we can manage. Pi over 2 up there. So that's going to be r squared. So we're going to get r cubed over 3.
Hold on.
Haven't you already distributed the r?
Wait, yeah.
Oh, do I have an extra r in
Yeah,
there?
you've got an extra r, because you pulled that from
No,
the top.
So this r up here, so here, this is our integrand, r plus r cubed. That's our integrand.
Then you have to.
And then we have to multiply that by y.
So that's r sine
But
theta.
isn't that what r...
Okay.
So here's the y that we're multiplying by right there. That's y.
Oh, and then we still need the Jacobian of turning into polar.
Yes. We
Right.
still have the r, the Jacobian, from converting to polar. Yep. Precisamente. Okay, so then when we distribute that r, we get r squared, which is r cubed over 3. When we integrate, distribute the r, that's r to the 4th, so that's r to the 5th over 5. Sine of theta is coming along for the ride. We're going to integrate 0 to 2 there, and we have a d theta. Okay, plugging in 2 looks like 8/3 plus 32/5. What the heck? 8/3 plus 32/5. Someone with a fancy calculator. Big 136 over 15? Thank you. Thank you. These modern calculators, super cool. Okay, integrate sine and we get minus cosine. And that's from 0 to pi over 2. Plug in pi over 2 and we get 0. Minus 1, so plus 1. So we end up with 136 over 15. So that is our moment about the x-axis, which gives us the y-coordinate of the center of mass. Okay, so this tells us then that y bar is equal to that moment divided by the mass, so divided by 3 pi. So, let's see, 3 does not go into there. So 136 over 45 pi. So that's our y bar.
That's also our.
That tells us then that our center of mass is going to be 136 divided by 45 pi, comma, 136 divided by 45 pi.
On my math lab, will they ask for that as like a.
Exact form.
Okay.
Yeah, they'll ask for
But
you.
as like a.
Ordered pair.
Yes.
Yep.
Yeah, I can't think of the word right now.
Ordered pair.
My mind's kind of blown.
Ordered pair. Oh boy.
What was the mass? It was 3 pi?
Mass was 3 pi.
Okay.
Mass was 3 pi.
So why exactly can you assume that the exponent?
So that is always the question that we have to ask ourselves. If you're not 100% convinced, then you should do the other one, obviously. So we're trying to figure out if the density function is symmetric on the region of integration. And so when we think about that, what I think about to myself is I'm thinking about these lines this direction. So I'm going to imagine these lines. And do you agree that the density right here, let's go up to that corner, and that corner, aren't those densities the same? Okay, one of them x is equal to 2, and one of them y is equal to 2, right? And then if we just pick a point here and then symmetric there, those two should have the same density, right? It's just that the x and y are playing opposite roles. And same thing, if you come down here, there, and there, those have the same density. Just x and y are flipped, but the density is 1 plus x squared plus y squared, so it doesn't matter. So you have to look at the function, though, not just the region. You have to look at the function and ask yourself, is the function symmetric along some line here? Yeah,
So
Eric.
how does it factor in when we have a shape like that, but we know that it has different densities on the half?
On the, did you say on the halves?
Right, so that's our
So-
section, but we know that the density is different. How does that factor in?
So if the densities aren't symmetric like that, then we would have to calculate m sub y also. And then when we divide m sub y by 3 pi, we would get the other coordinate. It would just be different. So we will certainly look at regions where the balance point could be right there, because it's more dense over here than over here. Definitely possible. So if we can't use symmetry of our density function, we just do the math. We find m sub x, we find m sub y, we divide them both by m, and we would find the point. Yep.
How do you know if it's like evenly distributed or not?
By doing some sort of analysis like I just did. So here I said, okay, well, I think x bar and y bar have to be the same, that they're going to be on this line. And so what I said to myself was there's the density here is the same as the density here. The density here is the same as the density here. The density there is the same as the density there. So the density seems to be symmetric about the line y equals x. So if it's not obvious that there's symmetry, then you can't use them. But here it's pretty obvious, you know, because the x and the y are just switching roles.
We can look at the density function, and we see it's x squared and y squared, so it should be matched, right?
Yeah.
It should be similar.
Yeah, so if they both have a square, you know,
Yeah.
if that density is 1 plus 2x squared plus y squared, then no. Then definitely no. Then no. All right, so 3 dimensions? Or should we do one more 2-dimension one? Nah, you're ready for 3 dimensions.
Do it.
Just do it. So the solid object also has a center of mass, and the center of mass is somewhere inside it, typically, unless it's a very strange shape. You can't have weird concave shapes where the center of mass is not in it. Okay, so same idea. We're going to find the moment, individual moments, not about coordinate axes, but we're going to find moments about planes. So we're going to find the moment with respect to the xy plane, moment with respect to the yz and the xz planes. And then same idea, we're going to take our moment, divide it by the mass to get the coordinate of the balance point, of the center of mass. So x bar is going to be found by using the moment that has no x in it, just like the previous slide. Right? X bar was m sub y divided by mass. So same notational convenience. So m sub yz is the moment about the yz plane. How far is a point from the yz plane? X. Its x coordinate measures how far it is from the yz plane. Right? The z coordinate measures how far something is from the xy plane. So let's see if we can muster this together. So same idea. The balance point, each coordinate, moment divided by mass. To get the moment about the yz plane, we have to multiply density by x. Moment about the xz plane, we multiply the density times y. Moment about the xy plane, multiply by z. So same idea, we keep multiplying by the distance to the object that we're trying to find the moment about. So here we go. Ellipsoid. So find the center of mass of the following solids, assuming, so they're going to be nice to us. They're not going to give us a variable density yet. It's already hard enough, right? Because we're going to be integrating with a multiplication by x, and then by y, and then by z. There's a lot going on. So we're going to the solid bounded by the upper plane, or excuse me, the upper half of the ellipsoid and the xy plane. Okay, so we're talking about the upper part of an ellipsoid, so let's go ahead and solve this for z. So the upper part of the ellipsoid, we're going to take the z squared, we're going to isolate it, take the square root. So we're going to have the positive square root for the upper part. So this will be the upper half of the ellipsoid. Let's factor out a 4. So we're going to get 2 times the square root of, that cannot be right.
No.
That definitely needs to be a 4. Definitely needs to be a 4. So 4 minus x squared minus y squared. Okay, so that's the upper ellipsoid. So now, can we use symmetry here? We're using a uniform density. We've got this ellipsoid, this half of an egg. Can we assume anything about x bar and y bar? Yeah, those definitely have to be the same. Everyone agree? So if we have uniform density, and we've got this ellipsoid, the center of mass has got to be on that vertical axis. So that cuts out a ton of work. So we're going to assume that x bar is equal to y bar is equal to 0. Right? So both those coordinates are 0. So the center of mass is going to be equal to 0, 0, comma. Let's see. We have to do that. Which m should we put here? Which moment?
XY.
So we have to have subscripts that don't include the z, since that's part of the z coordinate. Will?
Yeah, where do we gain x and y equals 0?
So the shape of our object is what's giving it to us. So we have an ellipsoid that looks like that. And so and because the density is uniform, that tells us that the center of mass must be somewhere along this axis.
Okay. So it feels like a wacky shape.
I see.
If it was a wacky shape, you've got to do all the math. No wacky shapes. No wacky shapes. Not yet. Not till your homework. Oh, it's coming. The wacky shapes are coming. Okay. So m sub xy and little m are what we're trying to find. So let's go find the mass first. It's always easier to set up the mass first. It's the easiest of the 3 integrals, or more integrals, however many there are. It's always the easiest one. And once you get the limits for the mass integral, they correspond to the limits for the other ones. So it makes most sense to go mass first. So integrating the density function, it's uniform. We're going to assume it's 1. And we're going to use just a double integral. So a double integral means that the integrand has to be the upper surface minus the lower surface. Upper surface is the ellipsoid, the upper half. So we're going to have 2 multiplied by 4 minus r squared. We're going cylindrical. Minus 0. And then our differential is r dr d theta.
Isn't that polar?
Yeah, I was gonna say.
Polar, cylindrical, same idea, right?
Just 2 dimensions versus 3, right?
Yeah, so with cylindrical, if we put a third integral here and put that as the upper limit, then we'd call it cylindrical. Cylindrical and polar are, kind of interchangeable when we're dealing with surfaces. So when we say polar, we mean the domain is polar. And if we use the word cylindrical, we're thinking that we're dealing with the surface.
So the derivative of polar, sorry, let me think of this. I gotta parse this. Like the derivative of a, what's it called?
Polar surface?
Of a cylindrical integral with the surface set as its bounds becomes polar, right?
Yes.
That's weird.
You just said, yeah, that's right. The derivative of a cylindrical integral becomes a polar function.
Okay.
Yep. All right, the limits for r, what do you think?
0 to 4.
0 to 4, does everyone agree?
Sure. 0 to 2.
Woohoo, disagreement. So fun.
I think it might be.
Okay, so what are we doing to look at that curve in the xy plane?
Setting z to 0.
Set z to 0. So we've got that ellipsoid like this. If we set z to 0, we're going to figure out what the intersection with the xy plane looks like. Right? The plane the xy plane has equation z equals 0. So we're going to plug in that. And when we plug that in, what we see is that we get x squared plus y squared equals 4. So that's a circle of radius 2. So our limits are going to be 0 to 2 for r. So that's in the xy plane. And theta, of course, 0 to 2 pi. That one's not so bad.
Although, one thing I'm confused about, we're integrating the density here, right?
Mm-hmm.
But if density is constant,
Yep, the density was 1.
then why are we integrating this exactly? Or
We're finding the volume of our solid object.
Oh.
So to find the volume of a solid object, you can do 3 integrals of nothing or 2 integrals of upper minus lower.
Because we're solving for mass here.
I did not skip a step. I did double integral of upper minus lower. That's how we first learned to find volume. Just like we first learned to find area by doing upper curve minus lower curve.
Alright, I just trying to figure out. Yeah, this looks like integrating volume, but okay. Oh, I see what we're doing here.
Mumble. It's all making sense in some plane. All right, so I'm going to fiddle with this integrand just a little bit. We're getting good at using fiddling techniques.
That's all math is anymore.
Yeah, it's kind of true. All right, so I'm just going to put a minus in there and a minus on the outside. Because I see that I need to use u substitution, if we let u equal 4 minus r squared, du is going to be minus 2r dr. So let's force it to be minus 2r dr. And if we put a minus sign there, we have to put a minus sign out there to make it equal. Keep the balance. Yes. My moment equals your moment. So then we can integrate using the power rule. We can also collapse the outer integral, correct? No thetas. So we're going to get minus 2 pi is the collapsing of the outer integral. And then, yellow quantity to the 3/2 multiply by 2/3. And r goes 0 to 2. So when all is said and done, we have minus 4 pi over 3 multiplied by 0 minus 8? Something like that? So that is our mass. Mass of this ellipsoid. This semi-ellipsoid? Or is it a hemi-ellipsoid?
Definitely a hemi.
Yes, Cargill?
So I just want to make sure I understand. Instead of like, you multiplied through by r with the square root, right? You just introduced, you sort of pulled it to the other side of the square root.
We're talking about that r right there?
Yeah, you still multiplied by 2 root 4 minus r squared. You just moved the r to the, or the 2 to the end.
I
and
moved
then-
the 2 over there and put it with the differential. When we
then
do u
negative.
substitution, if we let u equal 4 minus r squared, then du would be minus 2r dr.
Are you just skipping like the u sub step
Yeah.
by putting, okay.
U sub on the fly.
Okay.
We're capable.
Okay.
We're capable of doing U sub on the fly. It's kind of like the reverse chain roll. It's U sub without U sub.
Yeah, every time I
wait,
try to
there's
do it, I
more.
end up messing it up.
There is.
Okay, so that's our mass. Now we need our moment about the xy plane. Moment about the xy plane. So moment sub xy is the double integral of, or maybe we should write it as triple integral just to make sure that's how it was presented to us. Let's do this a triple first. So triple integral, the distance to the xy plane, z, and then we're switching to cylindrical, so it's going to be r dz dr d theta. And now up here we just did it with a double, but instead we're going to put this in the limits then. What was that? 4 minus
R squared.
4 minus r squared. Thank you. Thank you. So those are the z limits. Did we have to do that? No. We could have just come up here and multiplied by z, which is what we're about to get anyway in a moment. R is 0 to 2.
Just keep doing that.
It's freaking me out. So we get that. Okay, so now here is our problem. Well, maybe it's not a problem, but here's where the work is. We have to integrate that with respect to z.
Isn't that
That's
Not too bad.
That's
RZ
not
squared
because
It comes out easy.
Doesn't that the 2's cancel?
Yeah, it
and
just
then you
becomes
square
r
that,
times
which
the
is
square root of 4
minus
minus
r
r squared.
Yeah. Yeah, it's not going to be that hard, but,
Like,
but it's more work than. So, like right here, when we brought this down right away, we had, so this is just the place where we have to be careful. So multiplying this by z right here is, we can't quite do that. We have to be in the triple integral form. We can't shortcut it when we multiply it by z, because then we don't integrate by z. Okay, so yes, what you said is true. No thetas, so we get a 2 theta, or a 2 that letter. To that letter. 2 pi. So here we're going to get z squared over 2, and then r, let's write it all out, z squared over 2, r d theta, and then the z's are going from 0 to the upper surface, 2 square root, 4 minus r squared.
Who gets the d theta already?
Oh, d theta is gone, thank you. Let's get rid of that. No d theta. So we're almost there. That does make it look a lot easier, I guess. Okay, so 2's cancel, so we have a pi out in front, integral 0 to 2, and then the 0, nothing, so all we do is square that upper limit, right? So we get 4 times the quantity 4 minus r squared, all that's multiplied by r. So the 4 comes to the front, 4 out to the front, integrate, or multiply by r and integrate. So we have 4r, so we're going to get 4r squared over 2, which is 2r squared, minus r to the 4th over 4, 0 to 2. 8 minus 4 is 4. Multiplied by 4 pi is 16 pi.
Just do that over the other one.
So we're going to divide then. So our center of mass is going to be 0, 0, that moment divided by our mass, 32 pi over 3. Let's see. 0, 0. So we flip.
We get 3 halves.
And we get 3 halves.
Nice.
That is our center of mass.
This is like 0, 0, triple stack.
0, 0. 1.5. So that's our center of mass. Whatever that means.
Yep.
There's one more.
All right. There's one more.
Yeah.
Can we finish it? Let's see. Okay. So solid bounded by cone. This is going to be perfect. So we've got our cone and the plane z equals 0. Does everybody see that cone opens down?
Because it's negative x squared.
So when r is 0, so when you're 0 unit, if you imagine the xy plane, when you're 0 units away, you're up at 9. And then the further away you get from the origin, the closer you are to the xy plane, the smaller your z value is. What does r have to be in order to get to get a z value of 0? R is 9. So we have a cone that's at 45 degrees. So the height will be 9, the radius will be 9. Perfect. All right, and there's our variable density. So let's do a couple of things. Let's first draw the domain down in the xy plane. So down in the xy plane, we're dealing with a circle of what radius?
3.
9.
The radius will be 9. So everyone know how we got that? We set these two equal to each other. We get r equals 9. Right? If we intersect the two surfaces, z equals 0 and z equals 9 minus r, we get r equals 9. And is our density function symmetric on that domain? Is there any assumption that we can make? So right now we've got this cone. We've got this cone that's opening downward.
Actually, it looks like the only thing the density depends on is the height.
So that's what our surface looks like. Can we assume that x bar and y bar are the same?
Yes.
I don't think so.
So let me ask you this. So if you imagine your cone down like this, isn't it true that the density is the same at each horizontal cross section?
Yeah.
Because the density is z plus 1.
But it's not constant. It's different.
It's different, but
As
it's
you go
different in a
up.
symmetric way, right? The x bar and the y bar are going to have to be on that vertical axis because there's just as much density over here as over here on each layer. Each cross section has the same density all around it.
Because as you
So-
go up, you have the same amount.
Now, the going vertically up the z-axis, what's going to be different is that your density is increasing up here. So that means that the center of mass is going to be closer to the top, probably, although it's smaller. So we'll find out. But it's more dense up here than down there. So that's the direction where it's lopsided. The density is not symmetric along the z-axis, but it is symmetric along the way cross sections. So regardless of where you are in the base, the density is the same. So the center of mass has to be there for that cross-section. So if you imagine every cross-section's finding the center of mass of each cross-section, the center of mass of each cross-section has to be the geometric center because the density is uniform on that cross-section. Okay, so we can assume that x bar equals y bar, so that's good. So we need to figure out what m sub xy is again, and what the mass is. So let's do the mass first. So the mass, maybe it's best to always set it up as a triple if that seemed confusing to go to a double the last time. Okay, so mass is integral of density. And we'll use cylindrical, so we'll do r dz dr d theta. The lower surface is z equals 0. The upper surface is z equals 9 minus r. Theta is going to go 0 to 2 pi. R is going to go 0 to 9. So that's our mass. Cylindrical is super nice. No thetas, pi theta. Integrating with respect to z. So we have to integrate that with respect to z. So we're going to get z plus z squared over 2. That's all multiplied by r. The z limits are 0 and 9 minus r. And then we have dr. Plugging in 9 minus r for z. Okay, it's going to get a little messy here. So we have 9 minus r plus z squared over 2. So then we do our regular foiling business. Multiply by r dr.
How long did it take you to just be able to just bust that out?
About 4 seconds it just took.
No, shit.
I have my time.
I mean, like...
Lots of practice.
How much? Years?
Yes.
Of decades?
No. Well, last semester was the first time I ever taught this class.
Wow.
Joking.
Wow.
Oh. There was an almost.
No.
Wow.
Yeah, the first time teaching Cal 3 is hard. There's a lot going on, and you guys ask good questions. And everyone has a slightly different perspective. It's hard to know what's going on in Cal 3. It takes like 10 times before it makes sense. I would not want to be in the class I taught first. The first time I taught Cal 3, that'd be terrible. I mean, it's just hard. I took 3 hours of prep for every lecture that first time teaching it. Brutal. You know, it's like, yeah, go teach college algebra where it takes like, 3 minutes to prep instead of 3 hours.
Can we multiply that by 2 and combine?
Yes. So let's do that. If we factor out the 2, we're going to have pi 0 to 9. And then that's going to be 18 minus 2r plus, I guess we could have added this together in our head. We do other things more complicated in our head.
Yeah.
Okay, so what do we end up with? Let's distribute that r also. So square first. Let's make that r cubed. Linears minus 20r squared. Constants 99?
Yeah.
That just seems fishy. Pi times... Oh. Someone with a calculator, start calculating. All right, so we have to plug in the 9 into that and get, we can't finish this. Let's just get this number and then we'll do the moment on Wednesday. So somebody plug their 9 in there.
None of these come out to nice numbers.
They don't come out to nice numbers?
I have 324 pi.
324 pi total?
Yes.
All right. I'll double check it, and then we'll finish this one up on Wednesday. All right. We only have one more section in this chapter.
Just 3 points.
Right?
13.7
I think 13.7. So you guys get a test coming soon.
on Wednesday next week.
Yeah, it's a week from Wednesday.
No, we don't.
What?
November 2nd.
Wow, it's gonna be good for you. I mean, it's not like it's Halloween or anything. It's perfect.
Prepare for the first exam.
All right, that doesn't. Yeah, she got something different. I'm gonna put question marks here.
Hold on.
We'll double check that number.
Jim,
Yeah.
so then the test that's next week.